Previously, we discussed the position x, location along a number line, usually in meters, the velocity, which is the slope of the position versus time diagram, rise over run, change in position, distance, meters over time, seconds, meters per second, and acceleration, which is the rise over the run, the slope of the velocity versus time graph, meters per second vertical axis and seconds horizontal axis, meters per second or meters per second squared. So the process of slope taking allows us to go from position to velocity to acceleration. However, often we want to be able to go the other direction and go from acceleration to velocity to position. One motivation for that is that we work frequently with Newton's second law, which says F equals ma. So given the forces that apply for a given problem, we can solve for the acceleration. And given the acceleration, we want to find out what that implies for the velocity. And given the velocity, we want to find out what that implies for the position. So the way in which we move forward is actually to break apart these ratios of changes. So acceleration is the ratio of a change in velocity over a change in time. We're going to break those apart and write change in velocity is equal to take the dt from the denominator to the numerator on the other side. Change in velocity is acceleration times change in time. Likewise, break apart the ratio dx by dt, and small change in x is velocity times small change in time. Now, for these equations to be true, the steps need to be very, very small, and in fact, they need to be what's called infinitesimal. They need to exist in the limit that the steps are going to zero. However, we can still practice and get a little intuition and understanding about how this works by running through an algorithm that allows the steps to be small in some sense, but not infinitesimal. Let's take dt. I'm going to put it in quotes because it's really not an infinitesimal change anymore. It's a small change in some sense still. But let's take dt to be a fifth of a second. Let's take it to be 0.2 seconds. Let's also stipulate our starting values for the position and for the velocity. Let's say our starting position is going to be called 0. Let's say we're going to release an object from rest. So its initial velocity is going to be 0. We're going to drop it, and we're going to let gravity act on it. So let's say the acceleration, let's round, is 10 meters per second squared, the gravitational acceleration rounded, but in the downward direction. And what let's do then is run over an algorithm which takes incremental steps in time and updates the velocity for each step in time by the current value of the acceleration, and then updates the position for each step in time relative to the current value of the velocity. Let's take a 1 second wide time interval. Let's go from t, 0 to 0.2 to 0.4 to 0.6 to 0.8 to 1 second. So let's do time here in units of seconds. Let's also do updates to the velocity, and I'll put that in quotes because it's not necessarily an infinitesimal update. We're taking a little larger step in time so that we can work with it with pencil and paper. And let's also keep the accumulated velocity as a row of information. Likewise, let's track the dx, or delta x, small but not infinitesimal changes in position, and let's track the value of the position, and let's fill in this table. Okay. Now we know a few things at the outset. We stipulated that our initial values of velocity and position would both be 0. So let's fill in those spots. And then let's allow the velocity to begin to change. We're going to take steps in time, which are 0.2 seconds wide. So for every step in time, we multiply the step in time times the acceleration to get the step in velocity. Again, for this to be precise, we need the steps to be approaching 0, very, very small, but we'll spread them out a little bit and we'll get approximate results. So for a step in time of 0.2 seconds, with an acceleration of -10 meters per second squared. The result, these are going to be meter per second units. These are both going to be meter units. 0.2 times -10 is going to be -2 meters per second. Likewise, for every step along the motion here, our dv, since a is staying constant, a is always going to be -10. Things going to fall with constant gravitational acceleration. Since a is always -10, for every 0.2 seconds in time, we'll drop an additional 2 meters per second. So let's use that then to update our table. If we were at 0 and we dropped 2 meters per second relative to that, we're now at -2 meters per second. Now we're at 2 meters per second and we drop an additional -2, we're at -4 meters per second. Now we're at -4 meters per second and we drop an additional -2 meters per second relative, decrease an additional -2 meters per second relative to our existing velocity. We'll go to -6, then we'll go to -8, then we'll go to -10 meters per second. Now, how are our changes in distance progressing? Changes in distance will be values of the velocity times changes in time. Now, when we first release the thing, the velocity is 0. Now, we understand that that's only true instantaneously, and we're going to have some error accumulated in our calculation here because we're allowing somewhat larger steps in time to occur. But anyway, at the beginning, when our velocity was 0, 0 times 0.2 seconds would be a change of 0. When our velocity was -2 times a change of 0.2 seconds, we've got -2 times 0.2, -0.4 meters dropped in that interval. When the velocity goes to -4, -4 times a time interval of 0.2 seconds, that would be -0.8 meters. So we drop 0.8 meters in that interval. In the next interval, our velocity has decreased further to -6. -6 times 0.2, -1.2, -8 times 0.2, -1.6, and -10 times 0.2, -2.0. Let's see if we can make sense of that. What this is saying is that as we fall, we're falling faster and faster and faster. In other words, since we're falling faster, we cover a greater distance in the downward direction with each tick of the clock. So indeed, our steps are getting progressively larger. Now let's keep track of our accumulated position. We started at a position 0, and then we added 0, so that's 0. We started at 0, we decrease -0.4, so the total now is -0.4. We're at -0.4, we decrease 0.8 in the downward direction, a change of -0.8 relative to that. So we're at -1.2, -1.2, increase or decrease another 1.2, another 1.2 change in the negative direction, -2.4, and then -2.4, another 1.6 on top of that in the downward direction. That would be -4.0. So this says at the time of 1 second, we have fallen a distance of 4 meters, and our speed is 10 meters per second in the downward direction. Now we can actually check that. Let's check it. We can do this calculation actually in our heads exactly. How so? Well, we know that the gravitational acceleration in the downward direction is -10 meters per second every second. So after we fall in 1 second, indeed, the speed should be -10 meters per second. So that looks good. But how far will we have fallen in that interval? Well, we released the thing with 0 velocity, and at the end of the 1 second, its velocity is -10 meters per second. But it was only going that fast at the end. What was the midpoint? What was the average? Between 0 and -10, the average velocity for that time interval was -5 meters per second. If we're going 5 meters per second in the downward direction each second, and we do that average velocity maintained for 1 second, how far do we fall? The correct answer is that we should have fallen 5 meters, but the thing that we calculated was actually 4 meters. Why is our calculation a little bit wrong? Well, it's kind of in the ballpark. It's not terrible. It's an approximation. Why is it slightly incorrect? Because we were taking our steps in time to be finite rather than infinitesimal. If you redo this calculation, go back exactly through the same process, but take 0.1 second time steps, or get a spreadsheet out and take 20th of a second or 50th of a second time steps. What you should find is that as you make your time steps progressively smaller and smaller and smaller, running this algorithm, that's really what it is. It's a computer algorithm. Running this computer algorithm, you should get closer and closer to what we know to be the correct answer if you take your steps in time to be small enough. And that process of adding up the accumulated changes as the incremental changes approach zero size is mathematically what we call the process of integration. We'll continue to study that, learn how to do it graphically, and also learn how to do it in terms of functional forms. However, this process, which we've been discussing here, is in its own right very important. It's what's called numerical integration. It's the way a computer would do the integration process. In fact, we ran something that amounts to a computer algorithm on the paper.